Welcome back everyone. In this lecture we will see the structure theorem of finite abelian groups. In the next few lectures we will try to prove this important theorem. So let me first state the structure theorem of finite abelian groups. So in a plain language what it says, if you start with a finite abelian group G, then it must be product of cyclic groups. That's what it says. And there is some uniqueness also involved in the statement. So let me explain first of all how one can actually write down. So there are various version of this structure theorem. So let me state two versions and then we will actually try to prove both these versions are equivalent. Okay. So I will actually motivate by examples why these two versions are expected to be equivalent. Okay, let's start with the first version. So here is the structure theorem. So this is, I'm going to call it first version. So many books actually state it in different ways, okay, but we are going to see that all those versions are all equivalent. So you start with the finite abelian group, okay. Let G be a finite abelian group. So then the structure theorem actually asserts that this G can be expressed as a direct sum or direct product of a cyclic subgroups, okay, or cyclic groups. So then G can be expressed as a direct product. So when you deal with abelian groups, you call them as direct sum as well, okay, or direct sum of cyclic groups. Again, now we will put a condition on what kind of cyclic groups. So in the first version, we allow cyclic groups of prime power orders, okay, of prime power orders. So what is the meaning of that? So they are cyclic groups of order p power alpha for some prime p, okay. So very explicitly G is isomorphic to z modulo some p1 power e1 z, okay. Any cyclic group of order n, we know that it is isomorphic to z modulo n z. So if you take a cyclic group that has some prime power order, that will look like z power p power alpha z, okay. So this is one group. Then direct product z modulo some pk power ek z, okay. But note that here we do not assume these pi's are all necessarily distinct, okay. So some repetition is allowed. So P1 where P1 etc. Pk or some prime numbers, okay, and we assume that, okay, they are not necessarily distinct. They are not necessarily distinct, okay. So moreover, so whatever the decomposition that you are getting for this G, okay, in terms of this prime powers, okay, up to rearrangement, okay, you are allowed to actually shuffle them. So you are allowed to permute them, but up to the permutation, these exponents and the prime powers, they are all actually uniquely determined by G, okay. So moreover, this is also part of the statement. Moreover, okay, let me write it in blue. Moreover, these powers, the powers P1 power E1 etc. Pk power Ek, so they are uniquely determined by capital G. Okay, so what does it mean? In case G is isomorphic to some z modulo q1 power some e1 dash and so on, z modulo some q k dash e dash k dash z, then this number of these primes that appear, that will be same, and on top of it, so these now primes up to permutation, they must be same, and the respective exponents also must be same. Okay, so let's elaborate what is the meaning of uniqueness. Okay, this is the statement. So this is the first version of the structure theorem of finite abelian group. If you start with a finite abelian group, then that can be expressed as a direct product of cyclic groups of prime power orders. And that expression involving some prime powers, those prime powers are uniquely determined by G. That is what the theorem says. So now let's elaborate what is this uniqueness means. Again, we will actually prove the uniqueness. So what does it mean? Suppose G is isomorphic to some other tuple, like let's say Q1, some, let's call it something L1 Z cross etc cross Z some Q k dash L k dash Z. Okay, again assume that this Q1 etc Q k dash, they are all primes. Okay, so if this is what happens, then you already have this star, okay, called this is star. Then from star and double star, what you can say that this up to permutation, okay, so there exists sigma, okay, first of all k must be equal to k dash. So that means the number of factors that are there in this star, so that is first of all uniquely determined by capital G. So k equal to k dash, and then there exists a permutation sigma in Sk such that this q I power this Li will be same as p sigma I power E sigma phi for all from 1 to k. So that means just by up to permutation, these prime powers are all equal. So that is what it says. So G determines uniquely all these prime powers. So this is the first statement, first version of our structure theorem of finite abelian groups. Okay, so let me actually state the second version, but before stating the second version, let me actually do some examples, then it will be clear. So what is the meaning of the second version, why second version is naturally motivated from the first version. So before that, let us actually recall this fact. So this fact something we proved some time back. So this is actually implicitly uses this Chinese remainder theorem. So if you take Z modulo Mn times Z, okay, so then that will be isomorphic to Z modulo Mz cross Z modulo Nz if the GCD of this M and N are 1. Okay. So whenever you have two relatively primes, then if you consider the cyclic groups Z modulo M cross Z modulo M and Z modulo N, and if you take the direct product of them, that will be isomorphic to again a cyclic group of order Mn. That is what this statement says. So in particularly what you can do by induction, if you write this given capital N as some P1 power alpha 1 etc., some PR power alpha r, so then it is clear that this cyclic group Z modulo Nz is naturally isomorphic to Z modulo P1 power alpha 1 Z cross etc. cross Z modulo PR power alpha r Z. Okay. So indeed cyclic product of cyclic groups can be cyclic. When that can happen? It can happen if the orders of the respective cyclic groups are relatively prime. Okay, that is what you can prove from this basic facts. So this is the fact 1, this is the fact 2. So I will leave it to you to check both of them. Okay, so check the second is coming from 1. Okay, this is by induction you can actually prove. So, now using this on the first version of the structure theorem, you can play around and then you can come up with the second version. Okay. So, let us do one example and then we will state the second version. So, now what we are going to do, let us take this n to be 162. Okay, this natural number 162. So, we are going to look at the group abelian group of order 162. Okay. So, then what is the factorization of this? This is, you can see that this is 2 times 3 power 4. Okay. 3 square is 9, 9 into 9 is 81, 81 into 2 is 162, that is your number n. So, now for example, there are many interesting finite abelian groups that has this order. So, one such group you can take it to be, okay, as a first example, the cyclic group of order 162 itself. Okay. If you take z modulo 162 z, then you can see that that is one that is an abelian group of order 162. But since we have this factorization 2 into 3 power 4 is nothing but 162. So, you can see that this group is naturally isomorphic to z modulo 2z direct product z modulo 3 power z. Okay. So, 3 power is 81. So, 3 power 4 is 81. So, you can see that the product of these two cyclic groups is nothing but again a cyclic group. Okay. So, now interestingly this 2 and 3 power 4 combined, because 2 and 3 power 4 they are GCD is 1. So, this 2 and this 3 power 4 can be combined and then you can get this 162. So, that is what this says. So, let us look at another example, okay, then of the same order 162. So, for example, one can take first to the cyclic group z modulo 2z direct product with z modulo 3 square z and then z modulo 3 square z. Okay. So, look at it, this is indeed in the form of the first version. Okay. The first version says G can be expressed as a direct product of cyclic groups of prime power orders. Okay. So, but repetition is allowed. So, you can see that this is such example z modulo 2z and then 3 square that is a tuple that you are having. So, now what one can do, so now you can group them together and then make something interesting. For example, if you take this 2 and then this 3 square, both of them are relatively prime. So, we are allowed to combine them. Okay. So, then this becomes naturally isomorphic to z modulo 2 into 3 square. So, that is 18 z cross z modulo 9 z. So, now you have grouped, so that what happens, you have written it in some order, but this order says that 9 divides 18. Okay. So, once you have written it in this particular order, then you can see that this 9 and 8. So, this 18 and 9. So, this tuple is actually uniquely determined by this group G. Okay. This is the group G. So, there is no other way to actually write this tuple. Okay. So, this 18 and 9 somewhat uniquely determined once you write it in this form. So, this is the what somewhat gives you your second version of the structure theorem of finite abelian groups. Okay, let us do one more example and then I will state the second version. So, let us consider now z modulo 2z cross z modulo 3z and then cross z modulo 3z and then z modulo 3 square z. Again note that this is of the first version of the form that is there in the first version. All the cyclic groups corresponds to prime powers, and then this is again of order 162. Okay. So, now if you take this, then what you are getting, you can see that indeed you will be able to actually, if you want to write it in this form, okay. So, where 18 is bigger and the 9 is smaller, but 9 divides 18. So, that is the condition we wanted. Okay. So, here also that is how it is written. It is because there is only one component 162. So, we do not have two different components, but here in the example 2 you have two different components in the second version. But now if you take this particular example, you can see that to get such version you have to take this highest power of this 3 and then combine with 2, because 2 and 3 are relatively prime. So, in particularly 2 and 3 square are relatively prime. So, you are able to actually combine these two. So, then if you combine them, what you get? You get exactly z modulo 18z as before, and then cross z modulo 3z cross z modulo 3z. So, basically you have written it as, now this corresponds to 3 tuples 18, 3 and 3, but 3 divides 3 and then 3 divides 18. So, you have written it in this form. So, you note that these two are not, you can't combine them together, and similarly these two cannot be combined together because 18 and 3 they are not relatively prime. So, this is the max you can do. So, once you combine them this way, then you can see that these tuples, that what you are getting is uniquely determined by the group G. So, now using the first version, it is not hard to see how many possible non-isomorphic groups that you get of order 162, because the first version says any given this finite abelian group is can be expressed as a direct product of cyclic groups of prime power orders. So, that is of this form, this star. Okay. So, this P1, E1 etc. Pk, Ek, they are all uniquely determined by this G. Okay. So, because of that, if you think about it, once you know this factorization, that is 162 is nothing but twice 3 power 4. So, all matters is what is there in the exponent of these primes. Okay. So, now splitting them actually kind of determines somewhat unique finite groups of order 162. So, what I want to say, in case if you take this group that has order 162, so then you can see that if you write this G as direct product of prime powers z p1 power e1 z cross etc. cross z pk ek power z. So, if you write G equal to this z modulo p1 e1 z cross etc. z modulo pk ek z. So, then if you think about it, the cardinality of G is going to be this p1 e1 times etc. pk ek. Now, since the repetition is allowed, you can actually combine equal primes and then you can take the corresponding exponent. So, that it indeed says this Pi, it has to be either 2 or 3, because 162 is having only these 2 prime divisors. And if Pi equal to 2, then it forces Ei to be 1. Okay. And similarly, if Pj is 3, then Ej has to be now either 1, 2, 3 or 4. But whatever it is, so for some indices this Pj can be 3 because repetitions allowed. So, if you take the corresponding indices, let us say for E I1 etc. E some IR, all of them are 3, then if you sum the corresponding exponents, that has to be 4. So, basically that corresponds to partition of 4. Okay. And since this P1 power E1 etc. Pk power Ek, they are all uniquely determined by capital G. Okay. So, if you are interested in counting number of non-isomorphic finite abelian group of order 162, then that must be exactly equal to the partition of 1 times partition of 4. So, the number of abelian groups of order 162 should be the product partition of 1 times partition of 4. So, let us denote P of R by the number of partitions of R. So, what is the meaning of partitions of R? It is a tuple of sequence of numbers. Let us call it lambda 1 etc. some lambda a, which are in the decreasing order, such a way that this lambda 1 plus etc. lambda a must be exactly R. So, the tuple lambda 1 etc. lambda a is called partition of R if it satisfies these two properties. Okay. So, let us do one example. Let us compute what is partition of 4. So, if you take 4, you want to write it as sum of some smaller numbers, then you can see that so this 4 can be written as 4, and then it can be written as 3 plus 1, and then it can be written as 2 plus 2, and then 2 plus 1 plus 1, and then 1 plus 1 plus 1 plus 1 plus 1. So, there are 5 ways you can write 4 as sum of smaller numbers. So, that means, so in this specific manner where the sum of smaller number which are in the decreasing order. Okay. So, then partition of 4 is nothing but 5, that is what we are getting. Okay. So, both these conditions should be satisfied. So, with that condition you can see that partition of 4 is 5. So, now how many abelian groups of order 162 is there? Partition of 1 is just 1. So, it is 1 into actually 5. So, there are 5 abelian groups of order 162, non-isomorphic abelian groups. Okay. Non-isomorphic abelian groups of order 162 is exactly equal to 5. So, what are they? We listed already 3 of them. So, you can see that this one corresponds to, so this one corresponds to the partition, again empty partition, that is 1, and then this another partition 4. So, this is trivial, these two are trivial partitions. So, now if you take this one, you can see that this corresponds to again empty partition 1. Okay, let me put this colon here to separate them. Then you have this 2 2. Okay. So, what is about this? So, this corresponds to again 1 colon, so 1 1 2. So, that is what this is. Okay, 1 1 2, you write it as 2 1 1. Okay. So, now what's about other things? So, let us write all of them. So, 1 4, so this is the first one, and then 1 3 1, so that is the second one, again 1 2 2, that is the third one, and then 1 2 1 1, the fourth one, sorry 2 1. Then 1 1 1 1. So, this is the fifth one. So, let us see what will be the corresponding group. This will be just Z modulo 162 Z. And what is about this? So, this if you write it in the prime power form, it is Z modulo 2 Z cross Z modulo 3 power 4 Z. So, let us write it in the prime power form. So, this is Z modulo 2 Z cross Z modulo 3 power 3 Z cross Z modulo 3 Z. What is about this? This is Z modulo 2 Z cross Z modulo 3 square Z, Z modulo 3 square Z. So, what is about this? This is Z modulo 2 Z cross Z modulo 3 square Z cross Z modulo 3 Z cross Z modulo 3 Z. So, what is about the next one? This is Z modulo 2 Z cross Z modulo 3 Z. So now there are 4 copies of them. So you raise it power 4. So that's it. Okay, these are all non-isomorphic order 162 abelian groups. Okay, so now as we observed, we can rewrite given finite abelian group as a product of cyclic groups satisfying some very specific property. So what is it? So let us see in this example what are they. So in the first example it is going to be just 162. In the second example you can combine these two and then get something like this, z modulo. So 3 cube is 27, 27 into 2 it is 52 z, okay, 27 into 2, sorry 54 z. The third thing again you can combine these two. So then what you get is you get z modulo 18 z cross z modulo 3 square z. The fourth thing again you can combine these two. So this is going to be isomorphic to z modulo 18 z cross z modulo 3 z square. And the fourth one is going to be, again you can combine one of them, z modulo 6 z cross z modulo 3 z power 3. So note that you have written them all of them as product of cyclic groups, but in the very specific order. So it is in the decreasing order, and the number of elements in each component actually has some very specific. So the last component number divides the previous component number, okay, and so on. So indeed, so we are ready to now state this second version of the structure theorem. So here is the second version. So what it says, again as before, let G be a finite abelian group. So then you can prove that G is isomorphic to some z modulo a1 z cross etc cross z modulo some am z, okay, with the property that where a1 is divided by a2. So am divides am minus 1, am minus 1 divides am minus 2 and so on, a2 divides a1, okay. So with this condition you have this Ais, and moreover, so if you call this is star, okay, again with this property. So this is, you call it double star, and with this property, so this property is very important. So then moreover these Ais are uniquely determined by G with this condition, this with the condition this star. Okay, so you will be able to rearrange this prime power orders so that you can actually write this am divides am minus 1 and so on, a2 divides a1. So we will actually prove that these two versions are equivalent, and then once we are done with that, then we will actually focus on the first version and then we try to prove the first version, okay. But before proving anything, so we need to actually recall some of the basic properties of actually finite abelian groups, okay. So then later I will use them in order to prove actually all the results. Okay, so here is the first fact which we have actually proved it for any group, but anyway in the abelian group this can be simplified further, okay. So if you start with two groups, let us say H and K are two finite abelian groups. So some of them are true even for general groups, okay, but still because we are dealing with only finite abelian groups, I am only stating it for finite abelian groups. So you can immediately see that if H and K are two groups, then H direct product K is naturally isomorphic to K direct product H. Okay, so this is always true. So now let's state the second fact. So this is something about general group theory. Okay, if H and K both are subgroups of G, again assume G is finite abelian group and H and K are subgroups of G, then the following are equivalent. So what are they? The first thing is G is isomorphic to H cross K, and then the second thing is G equal to HK and H intersection K must be trivial, and of course both H and K being normal is dropped because we are in the abelian group setting. The third thing is if you take the order of G, then that is exactly the order of HK, and which is exactly the order of H times order of K. Okay. So now if you look at the subgroup HK, because H and K are normal in G, so HK will be a subgroup. So then order of HK being order of G will imply that G equal to HK. So now order of HK is nothing but R of K, R of H times R of K divided by R of H intersection K. If that is same as order of H, so then you can actually see that R of H intersection K must be actually trivial, which is 1. So that forces that H intersection K is trivial. Okay. So I will leave it to you to check this. These are all equivalent. So this is not that hard to actually verify. So here is another important fact, okay, so which is again very easy to verify. So this is the fact 3. So if you start with again G being a finite abelian group, okay, as I said, some of the statement even true for general abelian group or general group, but I am not worried about that now. So let some m is in n. So then consider this HM, so which is those element of x in G such that order of x divides m. Okay, so this is divides. So then HM must be a subgroup of G. So what is the proof? Proof is very simple. You start with x and y in HM. You can see that R of x divides m and R of y, which is same as R of y inverse, divides m. So now you want to calculate what happens to xy inverse. You raise it power m, you can see that since x and y both are in abelian group, so x power m and y power minus m is going to be identity. So that implies that xy inverse power m is identity. So that implies order of xy inverse also divides m. So that proves xy inverse is inside your HM, and HM is a subgroup of G. Okay. So for any m, you are able to actually get a subgroup which is explicitly given in this description. Those x in G such that order of x divides m. So note that if you have a subgroup of order m, then that elements of that subgroup actually satisfies this property. Okay. So in the finite abelian group, somewhat it's easy to produce lots of subgroups. Okay, so I will stop here, and then we will continue with the equivalence of the version 1 and version 2 of the structure theorem in the next class, and after that I will prepare slowly how to prove the version 1. Okay, once you know that they are equivalent, then it is enough to prove the version 1. So we will actually try to give like various proofs. For example, some of the basic results can be obtained easily from the Sylow's theorems. Okay, we will also try to directly prove in this situation almost, yeah. So the whatever that is guaranteed from the Sylow's theorem, how it comes for free in the finite abelian setting, because abelian setting is somewhat much easier thing to deal with. So one should be able to prove everything from the scratch. Okay, so we will try to do that in the next class. I will stop here. Thank you.